So we will continue today chapter 22 on initial value problems. So we have already covered several methods that can be used to solve such problems. The first one was the Euler method, which we are already familiar with. And we said that the disadvantage of this method is that it will just consider the slope in the interval ti plus 1 to be equal to the slope at the first point, which is not a very good prediction. This is why we try to come up with new techniques in order to find a best estimate of the slope, the average slope between ti and ti plus 1. The first method we went over yesterday was the Huygens method, which consists on considering that the slope, the estimation of the slope will be calculated as a mean between the slope at TIYI plus the slope at TI plus 1 YI plus 1 over 2. So it's the average slope at the two ends. Now, we have also, this can be enhanced by doing several corrections, and by not just considering the first yi plus 1 we get, because the first yi plus 1 we get is from Euler method. So in order to enhance this prediction, we can correct the value of yi plus 1. So we can repeat the Huygens method several times, and as we do corrections, our result will be better. So we will be able to reduce the error. So we have seen that once, for example, we find yi plus 1, 0, we can say now that the slope will be equal, we will update the slope to take it as average of the slope at the beginning point and the slope at the end point. And now, again, we go back to the starting point of the interval and we draw a second line characterized by a slope equal to the average of the slope at the beginning and last point. And then we can update yi. So this is the first correction. This is yi plus 1, 1. Now we can repeat this correction as much as we want, depending on the degree of accuracy required. So this is the first correction. Now we can proceed by evaluating the slope at this point. And always to evaluate the slope, all you have to do is to replace into the differential equation, because the differential equation is y prime function of t and y. So you can replace t and y by their values here. You can get then the updated y prime. And then once we calculate the slope, so this is, here we get y, and at y we calculate y prime. Then we can correct several times. So this is 1, okay, and this is y prime. So we evaluate again y prime at the corrected point to do another correction if we want. So again, by finding the slope now y prime at point 1, yi plus 1, 1, then we can find again a new average slope, and we will repeat this procedure. We can repeat it several times. So you can see here that as we repeat, as we correct, we are closer to the actual value of yi plus 1. So Huygens method can be more and more accurate by increasing the number of corrections. A more efficient method will be by considering the midpoint, because you know the midpoint will give a much better estimation about what is happening in the interval than using the endpoints. And if you remember, even in Simpson's rule, we have seen the importance of the midpoint. The midpoint can play, using the value at the midpoint will allow us to get a much accurate result with lower corrections, with lower number of corrections. And even we will see that the midpoint will just consist on finding it once without correction. So what is the idea now that we will introduce in the midpoint method? In the midpoint method, we will say, instead of always we should start from the beginning point of the interval. And we say, instead of going straight to ti plus 1, let us stop at ti plus half and see what is the corresponding y at this point. So the strategy using the midpoint method is to draw first a line of slope ftiyi from the beginning point and evaluate what is y here for a step of, so of course, since it's the midpoint, then the step will be equal to h over 2. So instead of going with a step h, which is the case we use in Euler method, we just go in with a step of h over 2. So now we are applying, if you want, Euler method just on the interval of length h over 2 to get what is yi plus half. And now, once we get yi plus half, the value of it, we can calculate using our differential equation what is y prime ti plus half yi plus half. So just we have, this is f represents y prime. So we can compute then, we can compute y prime at ti plus half yi plus half. And then when we do so, we can calculate, then we have the new slope. So we can get a new slope here. And then what we do, we say we will take as slope, instead of considering the slope at the first point, no, we'll take the first at the midpoint, because the midpoint will give us a much better idea about what is happening in the interval. So now all we have to do is to take a line passing by the first point, having a slope equal to the slope at ti plus half. And as you can see, we can approach in a very fast way the accurate value of yi. So this will be now yi plus 1. And we are very close to the actual value using midpoint method. So just doing one iteration with midpoint method can give much better results than doing several iterations with the Huygens method. And also, we can correct, we can proceed with corrections with midpoint method. But in general, when we say midpoint method, it doesn't involve corrections. If you want to do corrections, we can call it midpoint with corrections, okay? But in general, if they just tell you do the midpoint method, no need to iterate, you do it once, okay? Now we will see after in a more advanced technique that we can correct even for the midpoint and do something else to get a better accuracy. So now the idea is to compare all methods we have seen. So already we have calculated together, if you remember, if we will go over, we are doing the same example. We are going over the same example. Let us look at errors involved. When we use the Euler method, okay, we just did it, we are going over the same example with the same total integration interval from 0 to 4 with the same step size and of course the same function. When we did Euler method, and we did from step 1 to 3 to 4. Okay, we did 4 time steps. We end up with the following. If you compute, if you just draw the values in a graph, you can see what is the value of the error, and then you can calculate the true error. Okay, so as a relative true error at each point, because you have the true solution and you have Euler solution. We'll do this for Huygens method with correction, without correction, and for midpoint, to be able to try to compare these methods. Okay, so now yesterday we have done already Euler and Huygens method. So just as a reminder, when you use the Huygens method with correction, you should correct in each step. So if you remember here, this was development of a Huygens method for each interval. So for the first time step, I will do, they told me to stop for a criterion of a relative error between corrections of 2%. So here, if you evaluate here what is epsilon, so in general, you can evaluate here epsilon, but it will be compared not with the correction, with the predictor step, which is we got from Euler. So in general, we can consider that actual epsilon will start from here, because here we will start to compare corrections. So you compare correction 2 to correction 1 to see if you can stop. Then your criterion will not be satisfied, because now if you calculate epsilon as the absolute value of y12 minus y11 over y12, you will get a value larger than 2%. So you will say, no, I should not stop, I should continue, I should do a third correction. I do the third correction, I compute first y13, then when I compute y13, I can compare now the value between the true error, the error between these two, so the approximate relative error between y12 and y13, I will get it small, 1.7% smaller than 2. So I say, okay, I can stop here. So I can evaluate what is the slope phi, the corresponding slope, which is half f t0 y0 plus f t1 y13, and this will be my estimate of the slope. So now I can say that y13 is just y0 plus phi h, and I can stop here. Okay, so this is my third correction. I will go for it. I will find according to this my point, my y1 point. I am satisfied with my result. I can stop here. Now I move to the second time step. Okay, and I will repeat what is bad in Huygens method is that corrections will take computational time. So in each time step, I should repeat the whole procedure until reaching an error smaller than 2%. Okay, which will take time which will take a lot of time because I want to perform several corrections in each time step. We will see that with the Huygens method, we'll be able to achieve a relative true error that is very small in just one iteration. No need to iterate. And here I should do corrections in Huygens, while in midpoint I just do it once. I don't iterate. I compute. I can iterate, but it will not be called anymore midpoint method. It will be called midpoint with corrections, or also we will use a certain version of a method which will use the correction in midpoint and will also do something else to increase the order of accuracy. Okay, so in summary, until now, Huygens rule is better than Euler, but also it requires a lot of computations, especially if I do corrections. This is why we come up with another method that will be more accurate than Euler. So already Huygens is second order, while Euler is first order. So by using Huygens method, I increase the order of accuracy from 1 to 2. Okay, and now also the midpoint method will increase the accuracy from 1 to 2, but with lower computation. So as I told you, the whole idea is instead of considering that the slope, the slope that will represent the mean in the interval ti plus 1, instead of considering it as in Euler, we consider it just the slope at ti. In Huygens method, we consider it as the average of slope at ti and ti plus 1 with several corrections of the value of yi plus 1. In the midpoint, I just say I want to find what is the slope at the midpoint, and this will be my estimate for phi. As simple as that. So all I have to do first is to compute what is yi plus half. And as I told you, it's very simple. I just use, so it's like the first predictor step in Huygens. I use the Euler method. I just write that yi plus half is equal to yi plus the slope. So the first estimation for my slope will be the slope at I. Okay, so y prime I. Now, since I am advancing in a step of h over 2, so times h over 2, in this way I will calculate yi plus 1. Now, once yi plus half, once I have yi plus half, I can replace into the differential equation y prime. So I can evaluate f at ti plus half and yi plus half. And I consider that this will be my mean for the slope. So all I have to do now is to go back to my point. And now, instead of advancing at a slope of f at ti yi, I will advance at a slope f ti plus half yi plus half. And this will show that I will end up with much better accuracy using this method. Okay, so this method is easy and accurate. I can do it I have to do it in one step. So no need to correct because it was already efficient, and it is of second order instead of first order for Euler. So midpoint and Huygens both are second order methods, but midpoint from just one step will give us an acceptable result, while in general humans require several corrections to give a better accuracy. So in summary, these are the steps that I should do, no need to iterate. I will just first find yi plus half by using that yi plus half is yi plus h over 2 fti yi. Then I evaluate the slope at mid-interval, phi equal f to ti plus half yi plus half. And then I advance one time step by saying that yi plus 1 is yi plus the slope that I found here. This is my estimate for the mean slope between ti and ti plus 1. So yi plus 1 is yi plus 3 times h. So we will go over the same example again. We will solve y prime equal to 4 exponential 0.8t minus 0.5y. We'll integrate from t equals 0 to t equal 4 using the same time step of h equal 1 and with the same initial condition, which is y at t equals 0 equal to y0 equal to 2. So we are always proceeding with the same example so that we can compare at the end the results. So here, the first time step, so all I have to do is to apply, okay? So first to find y half, I say it's y0 plus h over 2 ft0 y0. And my function f is from the differential equation, which is 4 exponential 0.8t minus 0.5y. All I have to do is to replace t by t0 and to replace y by y0. I get the value of y half. Once I have y half, now I say I will evaluate what is f t half and y half. What is t1 half? You know that t1 half is simply h over 2. Okay. So we have h equal to 1. So t1 half will be 0.5. And y1 half is evaluated. We have just evaluated y1 half. So just we have to replace in the y prime equation, we replace t by 0.5 and y by 3.5. So we can get then phi that we will use to find y1. Okay, so this is the mean slope that will be used to go from y0 to y1. So now we can apply the formula that y1 is y0 plus 5 times the whole step h. Okay, so we can get we can advance to find t equal 1 what is y1. Once we got y1, now we move to the second time step. So for the second time step, we'll repeat the same procedure. Now we are working for t between 1 and 2. So the midpoint will be t of 1 plus 1 half. Okay, which is 1 second plus h over 2, which is 1.5. Okay, so now to find y at 1.5, it's equal to y1 plus again h over 2 times ft1 y1. Okay, so all we have to do then is to replace y1 by its value and to calculate what is f at t1 y1 by replacing t1 by its value, which is 1, and y1 by the value we got from the previous step. And then once we find yi plus half, we say that we should evaluate now the slope at the midpoint between 1 and 2. So it is f at t1 plus half, y1 plus half. Now, as we said, t1 plus half is is 1 plus h over 2, which is 0.5, so it's 1.5. And y at 1 plus half, we just evaluated here, it's 9.1141. So we replaced t by 1.5 in y prime equation, and we replaced y by 9.1141. Then we get the mean slope in the interval between 1 and 2, which is now 8.7234. Now, updating, now we are ready to find y2. So y2 is just y1 plus phi times h. So now we go the overall step, which is h, using the mean slope phi. And now again and again, so this is second time step is done. We move to the third time step. And once the third time step is done, we move to the fourth one. And then doing all of these operations, we can end up with y at 4. So we completed here. When we calculate y4, we are done. Okay, so again, in the third time step, first you get y 2.5, then you evaluate the slope at t 2.5, y 2.5, so you can update, you can find the value of y3. Once y3 is calculated, you move to the fourth step to find now y 3.5, and then once you have y 3.5, you evaluate the slope at it, and then you can get y4. So you can see that using midpoints method will require much lower computations than Huygens, because Huygens requires corrections. You can do Huygens without correction, but you will not get a very accurate result. Higher the number of corrections you do, better is your result. While for the midpoints, you can do corrections, but when we just say midpoint method without saying anything else, we just do it without any correction because it was already efficient. Okay. This is why we say we don't have to iterate in midpoint, since it's an efficient method that will give me a good error. If I want to have better accuracy, I can propose to correct.
دكتور
Yes.
هلا نحن we are doing these methods لأنه ما معنا ال original solution
أكيد.
لل differential equation.
أكيد ما
بس-
معنا solution. Exactly. We don't know what
بس
is. Yes.
yes
Okay.
بس الquestion إنه هو integrate يعني we are finding the points بس ما عم نوصل يعني آخر شيء بنعمل 2 points 2 points 2
yes,
points.
it's a discrete integration, منا continuous. Okay? And the purpose is to come with points, and higher the number of points you get, فيك تعمل fitting بعدين حسن. And if you want to come up with a function, you can find several points and then do regression or interpolation. Okay?
أو trapezoid أو هيدول
Yes,
السمسمة.
exactly. And you can do يعني هيدي ال procedure is discrete, منا continuous. You cannot come up with an integral function, a function that is exact. But you can come up with discrete points, and higher the number of discrete points, you can do fits, you can do regression or interpolation to compute what will be your function at a certain point.
Yes, doctor. Thank you.
Okay.
Doctor,
Yes?
in slide 35,
Yes. Yes.
yes دكتور لما جبنا هون ال y1 what you wrote about إنه ال h كانت t1 plus شي لأنه اتلاقى.
Okay, look, أنت when we calculated here y1 we calculated from the previous step, صح? Now you move to the
Yes.
second time step. In the second time step, you are working between t equal 1 second and t equal to 2 seconds. Okay? Since you are using the midpoint method, it consists on first finding what is y at the middle of this interval. Then you should find what is y for t equal to what? For t equals to 1.5, مظبوط?
Yes.
Okay, so what is t 1.5? It's t1 plus half plus h over 2, which is 1.5. How to find y at t 1.5? It's y1 plus half. This means that it's y of at 1.5 seconds. Okay, how to find it? I consider that I will start from the first point y1 that I have. So now the beginning point of my interval is y1. And I can know what is the slope at y1 because I have the equation for y prime. So I should evaluate the slope at y1, which is ft1 y1. And then to advance from y1 to y1 plus half, what is my step? It's h over 2. Okay?
Yes.
This is why I say that in order to get an estimation of y1 plus half, I do y1 plus h over 2 times y prime at point 1, which is ft1 y1. Okay? Now, once I find what is y1 plus half, I need to find what is the slope at this midpoint. So I need to find phi at the midpoint, because here in the midpoint method, I consider that the mean slope that will be used in the interval 1, 2 is phi at 1.5. So now once I got y at 1.5, I'm ready to evaluate phi at t1 plus half and y1 plus half. Already t is 1.5, I know it. And y1 plus half I calculated from the previous step. I just have to replace it. So I get phi. Now, once you get phi, what do? You want to compute what is y2. So how to compute y2? You say, now I will go back to point 1, but instead of using slope ft1 y1, I will use which slope? I will use the mean slope estimated as the slope at the midpoint, which is phi equal to 8.7234. So I will do a line with this slope. So I will move a step h to reach point 2. This is why y at 2 is equal to y1 plus phi, which is the slope at midpoint, times h. Okay?
Yes, clear. Thank you, doctor.
Okay. Now, another method that is much more accurate is the Runge-Kutta method, and it is a fourth order method. But its computation is a little bit more complex, and I will explain it in the following slide. So here, you have, the idea is, first, always I start from the first point. Of course, to start with, I have to start with the slope at this point, because already I don't know any other point. I know that this point is on my curve, let's say. I don't know where are other points. So to estimate other points, I should start from this one with slope k1. Now I say I will proceed first as, if you want, as Euler, but instead of going step h, I go step h over 2. So until now, it's exactly the same way that I proceed with the midpoint method. I draw first a line of slope phi 1. Okay, so this is slope phi 1 is equal to k1, which is the slope at point t1. I draw this line. Then I stop at ti plus h over 2. I evaluate the slope at this point. So until now, it's not different from the midpoint method. But in the midpoint method, I just, once I evaluate K2, I go back to point 1, and then I go from Ti to Ti plus H direct. While in Runge-Kutta method, what I do is, no, I correct again for the midpoint. As I told you before, when we just say midpoint method, it doesn't involve correction. But I can enhance it, of course, if I do correction. From here, Runge-Kutta method will first correct a first time for the midpoint. So now, instead of going directly to Ti plus H, I will stop again at Ti plus H over 2. And my slope here, the slope of this line will be equal to K2. So it's like the midpoint method, but instead of continuing to Ti plus H, I will stop at Ti plus H over 2. I will evaluate then the corrected, if you want, value of y at Ti plus H over 2. Once I correct y, I can find an updated slope, K3. Okay. And once I find K3, I go again back to the first point, and I draw a line of slope K3, but now I will take it, so I don't want to correct anymore with midpoint, I take it to Ti plus H. And now when I go to Ti plus H at slope K3, okay, then I will compute what is my K4. I find first what is my point yi plus 1. And once I find yi plus 1, I evaluate the slope K4 at yi plus 1. And now I have 4 slopes, K1, K2, K3, K4. My mean slope will be considered as a certain average between these, but I should pay attention. It's not an arithmetic mean. I don't have the same coefficient for all. No, I have a weighted average that is different for points. For the extreme slopes, I have just a coefficient of 1. While, because the midpoints are of high importance, they will be given a higher weight. So I have a weight of 2 for K2 and a weight of 2 for K3. Now, we will not go over the demonstration how we got this formula. We are just responsible of knowing that Runge-Kutta method is a fourth order method, and it is the mean slope in it is computed as an average, but with different weights for K1, K2, K3, and K4. Okay? So now we will repeat the procedure to summarize in a bigger figure that is clearer. So first I start with the first point. I evaluate the slope at it, K1. I do a line from this point of slope K1. I stop at the midpoint of the interval. I evaluate Y at this point, which will allow me then to replace into the differential equation Y prime to get what is K2. Once I get K2, I go back to the first point, and again, I draw a line of slope K2, and again, I stop. So this is, if you want a correction of the midpoint I obtain. I obtain a correction of the midpoint, then I correct the slope again, K3. Once I get K3, again, I go back to the first point, but instead now I stop. I do not correct again. I just do, if you want here, one correction for midpoint method. And then I take K3 and I proceed with step H until reaching then, until computing, to be able to compute yi plus 1. And once I compute yi plus 1, I evaluate the slope at it. And now I have 4 slopes. I calculated in this procedure 4 slopes. K1, which is the slope at Ti. K2, which is obtained from the midpoint method. K3, which is obtained from the first correction in midpoint method. And then K4 is obtained from going the step H as a slope K3. Now, once I get these 4 slopes, I say that the mean estimate of my slope in this interval Ti plus 1 is equal to 1 times K1 plus 2 times K2 plus 2 times K3. So it's a weighted average where I have different weights for points. The extreme points will have weight of 1, while midpoints will have weight of 2. So in total, the total weight is 1 plus 2, 3 plus 2, 5 plus 1, 6. This is why it's over 6. And then this will be my estimate of the mean slope between Ti and Ti plus 1. I will use it in order to find yi plus 1. Okay. So let us do in an example the RK4 method to integrate the same function. So again, we are working with the same function, y prime equal to 4 exponential 0.8t minus 0.5y. We are integrating from 0 to 4 using a time step of 1. And we start with an initial condition of y at t equals 0 equals to 2. So the first step will be to just compute what is K1. So to find K1, all we have to do is to say that K1 is f at t0, y0. So in y prime equation, we replace t0 by 0, and we replace y0 by its value, which is 2. We get K1. Once we have K1, we say now that we are ready to compute what is y 1/2. Okay? So now we say that y half is y0 plus h over 2 times K1, because we are drawing a line of slope K1 and we are moving a step of h over 2. Therefore, y 1/2 will be y0 plus h over 2 K1. We find y 1/2. Once we find y 1/2, we are ready to compute K2 to evaluate the slope at this point. So we evaluate slope at t half, y half. So we replace t half by its value. How to know what is the value? Okay, we should find what is the step. So here we have the time step is, so we have here a time step of 1. Okay, so since we are having a time step of 1, then t0 is 0, t1 is equal to 1. So t half is equal to 0.5. Okay. Now all we have to do is then to say that I will replace t half by 0.5. So here I will put to evaluate y prime half, okay, which is now k2. I should put instead of t 0.5, and I should put instead of y half, which I already calculated from the previous step. Okay, so now in this equation, I just when you replace t by 0.5, you will get 4 exponential 0.8 times 0.5, which is 0.4, minus 0.5 times this y, the y you obtained here, y 1/2, which is 3.5. So you get that k2 is 4 exponential 0.4 minus 0.5 times 3.5, which is equal to 4.2173. Now, once I get k2, I am ready to proceed. What should I do now? I should go